No, but please comment. I do need it for my research, guys. What research am I doing? I'm trying to use YouTube for like doing school. I don't think enough. Put that in the comments. Okay. All righty. Guys, this is on page 213. Go to page 213. We're going to do 16, 17, 18, 19, 20 right here. Okay. 16 is a problem about a seesaw. Remember, this says on torque. What's torque on the board over here? Force times distance times sine theta. And then if you balance something, both sides are equal. And then look, what's force? Mass times gravity, right? Okay. And you guys can actually get away with canceling the gravities. So, little secret, okay? You don't actually need to find force in some of these. You can just divide by masses. You can cheat a little bit, like with number 12, okay? Or number 16. Number 16's got a seesaw. There you go. Draw a seesaw. Okay. Draw people sitting on the seesaw. What do you think, Miss Rapp? Pretty good? Okay, this mass is 43 kilograms. This mass is 52 kilograms. This distance 1.8 meters, and this distance is unknown. Okay. Now, Ryan, you awake back there? All right, man. As you guys know, force times your distance times sine of theta for this side equals force times distance times sine of theta for that side. But Christian, there is a way we can make this easier on ourselves, right? Do we need to calculate the weight every time? We actually don't. Because is gravity the same on both? Yes. So really, it's just mass of this guy of 1 of A times distance of A times sine of theta. Now, are these guys both acting 90 degrees to the seesaw? Well, what's the sine of 90 degrees? 1. Okay. So you don't even need sine at this point. All right. So mass of B, distance of B. That's how much it's simplified. Make sense here, Ryan? You okay, man? You tired? So 43 kilograms. We are solving for distance of B. We're solving for distance 2. I'm sorry, I switched letters and numbers on you, Chris Parham. So times 1.8 meters divided by 52 kilograms is equal to my distance 2. 1 point, what'd you say? 1.5 or 1.49? I'll take 1.5. 1.5 meters. Okay, so that's just a little cheat code for you all. If you have objects acting both 90 degrees and then you just have gravity, you can cancel the gravities on both sides. Save you a little work. Okay? Make sense, Brady Reed? All right. Ready for number 17, Greeny? All right. Here we go. Man, that Christian kid is disruptive. My gosh. All right, number 17, a bicycle chain has a radius of 7.70. Okay, I'm not going to spend time drawing the chain and the gear wheels, but you guys get it. You know what a bicycle gear wheel looks like, right? With the teeth, okay? And then you've got the chain here, right? And then I put that in the comments. It looks horrible. Okay, so your 35 Newton meter force is pulling this way, right? 35 Newton meter torque, or excuse me, Newton torque meter force, blah, is pulling that way. Well, you need another force to pull this way, okay? And you have a radius here. So your radius is 7.70 centimeters. All right. What's that in meters? 0.0770 meters. Okay. Well, if they're balanced, then Torque of 1 needs to equal torque of 2. Well, they already gave you the force, right? Yeah. But we want to know the torque. So that means all we need is just one equation. Force times your radius times the sine of theta. All right. Is the chain operating perpendicular to the wheel? Yes. Ryan, you okay, man? Can you go to the nurse? All right. So it's operating perpendicular to the wheel here, and it's also operating perpendicular to the wheel here because it's made it stop. So we need that's sine of 90, right? Yeah. So all we need here is 35 newtons times 0.0770 meters times the sine of 90, which is just 1. Where's the what? What'd you guys get? Yeah, 2.695 Newton meters. Okay. Newton meters. Newton meters is going to be important, people, because when we get into things called energy and power, Newton meters are actually joules. It's actually energy. Okay. All right. Yeah. It's, in other words, it's got to be the same for. It's got to be the same on both sides. If you're pushed, yeah. If you have a 35 Newton, that's not that much force. So the torque is measured in Newton meters. So yes, you need that much force torque to stop it. Okay. Again, torque is not measured in newtons. It's measured in Newton meters. Okay. Newton meters. All right. So next, let us. Well, okay. I don't want to make this video too long. Let's try number 20. The challenge. You ready? Okay. Number 20. I wish I could just clear the writing without clearing the questions. I can't make that work, man. The spray bottle. Chase, that's amazing. That is amazing, Chase. Thank you. Okay. So this problem asks you about this bicycle pedal. The mass on top of this is 65 kilograms, okay? So it stands on the bicycle pedal. Now, look, if you stand on the bicycle pedal when it's like that, are you generating the maximum amount of force? You're not. It's not the maximum amount of torque at all. So the crank, you're drawing this. So the crank right here, the actual pedal itself is 0.170 meters, okay? And it makes a 45 degrees. So what does that mean? If this angle is 45 degrees, what's this angle right here? That's 45 degrees. Because it's not 90 anymore. What happened? It got reduced. It got reduced. But the wheel right here is 9.70 centimeters. Well, don't we need it in meters? So 0.0970 meters. So what it's asking you is, what force is present between the wheel and the chain? Okay. Now, obviously, it's not going to be as much as what your weight is, right? Because it's not where? It's not 90 degrees. It's not flat. You don't push with as much torque when the pedal's up here, do you? But we still use the same equation. So torque 1 equals torque 2. Okay? So we'll call this force 1. We'll call this force 2 over here. All righty. So what is our equation here? Force 1 times distance 1 times sine of theta equals force 2 times distance 2 times sine of theta. All righty. So Christian, we will need to use gravity at this point because we don't know the masses on both sides. Okay. All righty. What angle are we going to put in for this sign? Well, look at this. Okay. Look at this. The pedal. Okay. The pedal and the gear wheel. The pedal and where the gear wheel is actually acting are, what is this angle right here? This is 90. So we're going to use sine 90 for that one. So we don't know the force 1. We're trying to find it. The distance 2 is distance 1 is 0.0970, and this is sine of 90. Okay. But on the other side, we have force. How are we going to find the force? Mass times gravity. So on the other side, we have force 2, which is what? Gravity 65 kilograms times 9.8 meters per second squared. I'm sorry for the sloppy writing. Times this distance here, Greenie, 0.170 meters times the sine of 45 degrees. And you can comment on how sloppy that is. All right, Ryan, I want you to calculate this side and divide it by this side. Okay? Calculate that side and divide it by that side. So in other words, all this stuff in purple right here, Indigo, goes together. And you're going to divide it by this side in green. I'm sorry that it wrote it like this. I didn't have much space. It's Ariana's fault. She made me move the thing bigger. All right. Multiply and divide, guys. Sir? 789. 789 newtons is good. Did you divide by sine? No, well, that's obviously 1, right? Did you multiply 65 times 9.8 times 0.17 times sine of 45? You must have not put a parenthesis somewhere. Okay? Times 0.170 times parentheses 45 sine. Are you in degrees? He's in radians. All right. I want you guys to try right now numbers 18. Just do number 18 as practice. Okay? You can also do 19, but I want you to do 18 right now. And then in a minute here, we'll make another YouTubes with angular velocity and centripetal force and all that. All right.